All right. Welcome, everyone, to today's seminar. Today, I'm happy to have Katherine Davidson with us. Katherine is a PhD candidate in the Department of Space Science from the University of Alabama in Huntsville, where she's pursuing research on ionosphere-thermosphere coupling using both ground-based instrumentation and the TIE GCM model. Katherine received her BS in physics from Auburn University, where she did research on geomagnetic storms using twins data and CME simulations. In her free time, she enjoys reading science fiction novels and traveling. Today, I'm delighted to have Katherine here with us to talk about investigating the dependence of high-latitude thermosphere winds on geomagnetic conditions.
Okay, thank you for the introduction. I'm going to be talking about the dependence of thermospheric winds on geomagnetic conditions, but also just be talking more broadly about winds and their forces as well. So just a quick introduction into the ionosphere-thermosphere system. So the thermosphere makes up the upper portion of the atmosphere and hosts the neutral particles there. And the ionosphere is actually made from ionizing the thermosphere. So it is the ionized portion of the upper atmosphere. And because the ionosphere is just the ionized thermosphere, they exist in the same region and interact with each other quite often. And these coupling processes are done through collisions between the two species. So to talk more about the high latitude ionosphere dynamics and sort of how the ionosphere is driven, the ionosphere is actually electromagnetically coupled to the magnetosphere. So whatever dynamics are happening in the magnetosphere will be mapped down to the high latitude ionosphere and be imposed upon there as well. So when we have southward IMF conditions, the magnetic field of the solar wind will reconnect to the magnetic field of the dayside magnetosphere. And this will open the field lines, and the field lines will be pushed backwards towards the night side to the magnetotail. And this will squeeze the magnetotail and cause another reconnection event there, sending the field lines back to the day side. And this is called the Dungy plasma convection cycle. And this convection cycle is reflected in the ionosphere by having an anti-sunward flow over the poles. This is the equivalent of these field lines being pushed back towards the night side. And then it has a sunward return flow on the dusk and dawn side in the auroral region. And this is the representation of the field lines reconnecting in the night side and being pushed back towards the day side. And this is known as the two-cell convection pattern. So anti-sunward over the poles, and then it'll be westward return on the dusk side and an eastward return on the dawn side. And usually these changes are reflected within minutes because the electromagnetic force there is really one of the only forces acting in the ionosphere. It changes very quickly when the magnetosphere changes. The neutral winds are much more complex than the ionosphere. It is coupled to the ionosphere through collisions, so we do see some of that momentum being transferred from the ionosphere to the thermosphere, but there are a lot more forces acting on it as well. So it's also subjected to temperature pressure gradients. This is usually on a global scale, the day to night pressure gradient that the neutral winds are being subjected to. The Coriolis force also acts in the westward direction on the northern hemisphere, and there's advection forces and viscosity forces as well. So it's a lot more complicated to try to track the neutral wind behavior. It can be subjected to many forces at once. And yeah, this makes it a lot more difficult to study. We can get kind of a global statistical pattern of neutral wind behavior, though. So this study shows the statistical patterns of neutral wind behavior, and because of the coupling between the ionosphere and the thermosphere, the neutral winds actually mostly follow that two-cell convection pattern. But This will be modified by the presence of other neutral forces. So as you can see in this figure here, this is a polar plot looking down onto the poles of the neutral winds. And we can see this nice westward dusk cell here, the neutral winds following the ionospheric convection pattern there. But on the dawn side, we don't see this nice convection cell, and that's because the Coriolis force, again, acts in the westward direction, so it enhances this dusk cell, but it inhibits the dawn cell, preventing that flow. And this pattern also has a delayed response to ionospheric convection. So because the neutrals are so much heavier, the thermosphere is so much heavier than the ionosphere, it takes a lot more effort to get the thermosphere to flow. So the neutral winds are actually really important for dissipating the energy and mass deposited into the high latitude ionosphere during periods of enhanced geomagnetic activity. This was kind of discussed a lot more in Dan's talk that he gave earlier this year, I think. So for more details about that, I would go ahead and watch that. So one of the things that neutral winds do is that it modifies the Joule heating rate. This Joule heating rate is pretty important because increased heating will actually cause the thermosphere to rise and upwell. And this will increase the neutral density at higher altitudes, aka altitudes where our satellites are flying. And this increased density increases the satellite drag and leads to things like the SpaceX launch failure in 2022. So this study by Dan shows the Joule heating rate without the neutral winds here, and then with the neutral winds here. And you can see once you add the neutral winds to the Joule heating rate, it is quite modified. It is increased in the dawn side and decreased in the dusk side. So that is very important to understand for understanding satellite drag. The neutral winds also redistribute mass. So the heating that is put into the upper atmosphere, it actually creates really strong pressure gradients that move winds from the poles to the mid or low latitudes. And so this will redistribute any of the density deposited in the high latitudes to the low latitudes and lower that atmospheric density at the high latitudes. And this is also kind of known as the traveling atmospheric disturbances. So even though the neutral wind behavior is really important for dissipating all of this energy and kind of being the mediator for space weather effects, it's not very well understood. There's a lot of open questions, but the ones I'm going to be focusing on today are the neutral wind response time. We are not quite sure what the lag is between the plasma and the neutral wind response, even though we know there is one. And we also don't really know the controlling factors of that response time. So even if you can say that ion drag is that dominant force between the ions and the neutrals, ion drag still relies on the plasma speed, the wind speed, neutral density, ion density. So it's still not clear what the controlling factors are for that response. And I said, even if you can pinpoint one force for the neutral wind behavior, and that's because doing this is actually quite difficult. There's still a lot of questions about what the dominant forces are in the thermosphere that's driving that neutral wind behavior. And so studying and answering all these questions is important because a better understanding of the thermosphere dynamics actually leads to a better understanding of space weather. So one thing that's of particular interest is the neutral wind response time. And that's because this indicates the strength of the ion-neutral coupling. And this ultimately provides a time scale of the mediation of space weather. So how quickly the neutral winds respond to changes in the ionosphere tells us how quickly that energy is going to be dissipated from the high latitudes to the mid to low latitudes, or how quickly that joule heating rate is going to increase or decrease the density. And this is historically difficult to calculate just due to lack of measurements. And so I'll be talking a little bit about the three primary methods that have been used in the past, sort of working our way through time, what people started with, what people are working on now. I find the history of this pretty interesting because just coming into grad school and looking back on all the methods that people were able to come up with maybe limited data or computational methods is just pretty fascinating. So starting with the e-folding time, it actually started, there's two types of e-folding time calculations. One focuses on the density and the other focuses on the flow. So focusing on the density calculation first, this was introduced by Baron and Wand in 1983, and it's based on the neutral momentum equation. So it's basically taking the equation that had the pressure gradient, Coriolis, all those forces, and just setting them all equal to 0, except for the ion drag term. This is based on the assumption that during geomagnetic forcing, the ion drag is going to be the dominant force on the neutral winds. So this ended up with an equation that was based on the neutral density, the ion density, and then the collision frequency between the two. Some empirical models were used to estimate the collision frequency and the neutral density to get a response time that relied just on the ion density. And this resulted in a response time, a theoretical response time of 38 minutes to over 6 hours, which is quite a long range there. And then Ponthieu et al. In 1988 actually used satellite data to plug in the numbers for the neutral density and the ion density, but still used a empirical calculation of the collision frequency to get a response time of 1 to 3 hours. So this method already was a little bit difficult because calculating the collision frequency is pretty tough. It relies on many different measurements of the ionosphere and thermosphere that we just didn't really have. And so that's why these methods usually used some sort of assumption or empirical model for that collision frequency. So instead, the e-folding time was modified to use the plasma and wind velocity measurements instead. So instead, we get this equation that just relies on the plasma speed, the wind speed, and then the time derivative of the wind. And this was a lot easier to get measurements of. So this study by Koch in 2001 took satellite data of the plasma speed and wind speed and calculated an average e-folding time of 1.8 and 3.3 hours for geomagnetically active and quiet periods, which is still quite a long time. So some people more recently, Joshi in 2015, came up with something called the time-lagged correlation analysis. So instead of making an assumption about the forcing on the neutral winds, it's just based on observations of the plasma and wind velocities. So what it basically is just a cross correlation of the plasma and wind speed time series data. And this is based on that assumption that if the winds are following the plasma pattern but are delayed, then you're going to be able to match those patterns by a correlation coefficient. And the time lag of the maximum correlation between the two species is then the neutral wind response time. So this method often results in a shorter response time than the e-folding time. So they actually performed both calculation methods for an event and saw that the lag time was 84 minutes versus 125 minutes. And I'll talk a little bit more about the comparison of the two lag times a little bit later. And also more recently, just observational analysis has been done to calculate the neutral wind response time. So this is basically just a qualitative determination. So these plots here show the plasma and neutral velocity time series data. And it's basically just taking the difference between the maximum perturbations of both. So, this top plot has a 1 to 9 minute difference between the maximum speeds here, and this plot has 15 to 26-minute maximum difference between the two perturbations. So this also yields a shorter response time than previous calculation methods, from minutes to tens of minutes. But none of these response time calculations were really done on a statistical scale, and it's quite difficult to compare all of these methods together because, like I said, they're only done for a case-by-case event, and if the observational analysis is shorter for one event, then the e-folding time, they weren't done, those calculations weren't done for the same event, so it's difficult to say which one of them are correct. And all of these response times also have some limitations. So we really saw the need for a new response time calculation. So the e-folding time, the assumption that ion drag is the only driving force is not always accurate. There's always going to be some presence of a pressure gradient or Coriolis force acting on the neutral winds. And the time-lagged correlation analysis, because you're cross-correlating the two species, you really only get one response time, one maximum correlation for the event. And this singular response time is not really suitable for the dynamic auroral region, where the forcing and the response times might be changing on 30-minute bases. And the observational analysis, of course, is just subject to human error and might not be suitable for a very large statistical study. So what we came up with is the weighted windowed time-lagged correlation, which is such a mouthful, and it was my first paper, so that will probably haunt me for the rest of my life that I couldn't come up with a better acronym for that. But what we basically did was we performed that time-lagged correlation analysis, but we did it on 2-hour sliding windows. So for this event here, you can see this window is from 8 to 10 UT instead of doing it all the way from 7 to 12 UT. And this provides the time evolution of the e-folding time without the assumption of what the dominant force is. So you kind of get the benefits of both response time calculations there. This method can often occur in double peaks, like this curve here. And that's because the correlation calculation only relies on the magnitude, or it only relies on the shape of the curves and not the magnitude. So you can see this peak here at 75 minutes. When you lag the wind data in red and plot that against the plasma data in blue, you can see the two species are actually moving in opposite directions. One is westward and one is eastward, and that's not actually a good fit. So instead of having to go through each peak and manually identify which one was better each time, we decided to multiply each of these window curves by the time-lagged correlation of the entire event. And this is because we still want to consider the long-term trends for the event. So as you can see here, after we applied the weighting, that second peak was eliminated, leaving just the first peak at 15 minutes, which gives a much better visual match than the 75-minute peak. And this method to also showcase the time evolution of it, you can see for this 8 to 10 o'clock window, we have a 15-minute delay, which matches this eastward response right here pretty well. But towards the end of event, you can see that the delay, the wind was delayed a little bit too far towards the end here. And the response is actually a little bit faster as the event goes on. And so looking at the 9 to 11 o'clock window, you can actually see that the response time is now only 5 minutes, which much better matches this wind and time series, or wind and plasma series at this time period. So using this calculation method on a statistical scale, we look at substorm events because we want to look at sudden changes in the plasma flow and see how the winds respond to that. And those happen most often during substorms. So we apply the weighted windowed correlation calculation, and we take the response time of the 2-hour substorm onset window. So for example, for a 10:30 UT onset time, we use the window from 9:30 to 11:30 so that the substorm time is at the midpoint of that window. And we can see that the average response time is 16 minutes. So that is a pretty short response time statistically than some of the previous response times that showed on the order of hours. And so now we want to take it one step further and determine what differentiates these groups of events. So we split these events into short and long response events based on this response time, the average response time. So these events are all less than the average response time, and these events are all greater than the response time. And we want to know if there are any differences between these two and what caused the faster event, faster response time versus the slower response time. So we first look at some case studies of the events that we have. So this is a short response time event. You can see that the plasma and the wind here, again shown in blue and red, are following each other, or the wind's following the plasma time series pretty well. So it's pretty tightly coupled here. The response times are also very short, 15 minutes or less. And we look at the geomagnetic conditions on the left-hand side to see if we find any similarities between the short response events or differences between the long response events. And what we kind of noticed the trend of is that the short response events pretty often have this southward IMF turning before substorm onset. This condition is usually required for substorm onset that allows for that magnetotail loading in order to reconnect on the day side and initiate the substorm. We also noticed that a lot of these events have a really small SIM-H index, and this is a measure of the ring current, which shows any geomagnetic storm activity. So this event has no enhanced ring current, and it also has a pretty quiet AE index. This is a measure of the auroral electrojet, so it shows the strength of substorm activity. So pretty quiet before the substorm onset time. And then we also have an enhanced electron density here at onset time, which of course electron density increases will increase the collision rate, which will decrease the response time. For our long response event, you can see the response times here are around 25 minutes or more. It's actually shorter at the substorm window, which was pretty interesting because that indicates even for long response events, we do see a faster response time with the presence of the substorm forcing. And the geomagnetic conditions show a pretty weakly directional IMF at the onset time, though it was southward for a few hours before onset time. We have an enhanced SIM-H. It's not quite geomagnetic storm levels, but perhaps in the recovery phase of a weak geomagnetic storm. And we also have a pretty active AE index before onset time. The precipitation is enhanced throughout the night, but it is sort of bursty-like and not quite as concrete or solid as the precipitation for the previous event. So seeing if we see this type of trend on a statistical scale, we do a superposed epoch analysis of these geomagnetic conditions. It's really important to note that these are the average conditions. So this is not a perfect representation of each event, even though the superposed epoch analysis could show this trend. One individual event might be somewhat different or stand out. But this is just the average conditions for both our short responses and our long responses group. So the things that kind of stood out was that the short responses do have that southward IMF turning before onset time and quiet geomagnetic conditions. The long responses have an extended period of southward IMF before onset time, but kind of non-directional at onset time and enhanced geomagnetic conditions. What this may mean is that the thermosphere may be more active during the long responses and therefore might be harder to turn, might be harder to for the ionosphere to force it in a different direction if it's already enhanced in one way or another. This thermospheric preconditioning is something that is a little more difficult to look at because the nature of our data is optical, so we only have thermospheric wind data at night. So we might not be able to look at the preconditioning because we just might not have any data before the event time. We also do this superposed epoch analysis for the electron density, and it's immediately pretty clear that these short responses have a larger electron density, especially at onset time and shortly before onset time. And this electron density increase, again, impacts the collision rate, which affects the ion drag force, strengthening the force and therefore making the neutral winds respond faster. So moving on now to kind of the forces that dominate the neutral wind. Of course, this is also difficult to calculate. Some people have tried to do it observationally, maybe by proxy. So I brought up these figures earlier that has the comparison of the time lag with the E-folding time. And sort of the theory was that because the E-folding time only relies on ion drag as a force, whereas the time lag considers all of the neutral wind forcing. If the E-folding time is longer than the time lag, that would maybe indicate that the ion drag force might not be the dominant force, since other forces are clearly needed to explain the observational response time. This is a little difficult to do because the E-folding time relies on that V minus U term, so the plasma speed versus the wind speed. Because the plasma speed is always much, much faster than the wind speed, that E-folding time is always going to be large, and it might not be a real indicator of the strength of the ion drag force. And so the best way to kind of get around this is just make use of global circulation models, or GCMs. So this has been done in the past. The GCMs have been used to calculate thermospheric forces because you can just get so much data out of the GCMs, or so many parameters out of them. You can actually calculate all of the individual thermospheric forcing terms. So this study showed that the main forcing balance is between the ion drag and pressure gradient terms at F-region altitudes. However, this was calculated for a steady state thermosphere and not a real-time run. And another study did a similar thing, and they found that the winds above 123 kilometers are sustained by the pressure gradient, Coriolis, and advection forces. So a very different result than the previous study. However, this was also calculated for an idealized steady state system and not a real-time event. And how the GCMs are driven also matters a lot. So the GCMs rely on high latitude convection and auroral precipitation patterns. These things will affect the neutral forcing because the convection will control the ion drag. The auroral precipitation controls the ion drag and the temperature gradients and so on. So these things will greatly change the simulated neutral winds. And this study actually compared a number of different convection and auroral precipitation patterns driving the GITM model. And you can see the winds change quite drastically between all of the events. So what we do, we did a model data comparison of the simulated neutral winds from TIGCM using empirical model and a realistic model. And this is the empirical model in the top plot here, the realistic model in the middle plot here, and then the observed winds from the ground observations that we have. And we also plot the errors in the bottom plot here. So the solid curves are the empirical errors, and then the dashed curves are the realistic errors. And we calculate an RMSE, but we also do the correlation between the simulation and the observations. And this is because we want to know the magnitude error, but we also want to specifically look at the structural error because we want to know how well the model is replicating the neutral wind structures that we see. And so the realistic driver actually yielded a higher magnitude error, as you can see in the dashed curve here, but a better spatial correlation in the zonal direction. So this kind of points to why we need to do more than one error calculation, because if we were relying on RMSE alone, we would say, okay, well, the realistic model has a higher error, let's not use that. And that is not the full picture, so it's really important to sort of look at multiple error calculations there. And the empirical driver also really overestimated the meridional wind speed, but the structure between the empirical and realistic compared to the meridional observed winds are pretty similar, as you can see in the red curves there. So now we can sort of look at the thermospheric forces for the two model runs and see, one, how the model runs are affected, or the forces are affected by the empirical drivers or the realistic drivers, and also look at what the dominant drivers are. So the forces here are the pressure gradient force, ion drag force, Coriolis, viscosity, horizontal advection, and vertical advection. And we also have the total force here, and this total force is the cumulative sum of all of these forces. And so we identify the dominant force by comparing the structuring of the total force to the individual forces and kind of see which features are most reflected in the total force. So for the empirical run in the zonal direction, we definitely see that ion drag is a dominant force. You can see these forces here are sort of replicated in the total forcing structure. But then Coriolis force kind of becomes a more dominant force towards the end of the event there. And in the meridional direction, we get that the pressure gradient and the ion drag are dominant drivers here. And we also see that the total meridional force is pretty strongly southward for the beginning of the event, which caused the oversimulation of the southward winds. These oversimulations of the southward winds also resulted in our strong Coriolis force here. So the zonal Coriolis force is dependent on the meridional wind speed. So this total forcing might not actually be that accurate because this force is oversimulated. And moving on to the realistic driving of the thermospheric forces, we definitely see that the ion drag is a dominant zonal force. And we also have contributions from horizontal advection. And so because ion drag is a dominant zonal force, realistic convection patterns are very important for simulating the neutral winds. And that's why our realistic driver better replicated the structures of the neutral wind, the observed neutral winds. And we also see that the pressure gradient is a dominant meridional driver here. And we see sort of periodic wave-like behavior in the pressure gradient. And this is most likely associated with TAD, traveling atmospheric disturbance. And this sort of periodic behavior is most likely what prevented the realistic driving meridional winds from becoming too strongly southward like the empirical driver was. And so now hopefully we understand the neutral wind behavior just a little bit better. Still not a complete picture, but we can say now that the neutral wind response time statistically is on the scale of tens of minutes. The controlling factors of the response time, it somewhat depends on the geomagnetic and thermospheric preconditions, but it also really depends on the electron density. And the thermospheric forces most responsible for driving the neutral winds are the ion drag and horizontal advection forces in the zonal direction and the pressure gradient in the meridional direction. So thank you for your attention, and I'll take any questions now.
Thank you, Catherine, for a really cool talk. It was really neat to see how those two things and two different systems interact. I had a quick question. You were looking at the short and long-term timescales, and then you mentioned that convection played a pretty important role. Between those two in the superposed epoch analysis, do you think that could be the difference between substorms and sporadic convection versus steady magnetospheric convection and strong driving?
Yeah, it's actually interesting because we kind of saw with the short and long response in superposed epoch analysis that the long responses are kind of more associated with like enhanced geomagnetic activity and recovery phases of geomagnetic storms. This is kind of unexpected because we do expect the sort of driving to be stronger for those periods. So this is where that like thermospheric preconditioning might play a role, where if the thermosphere is more enhanced and more active, it might actually take a little bit longer to respond. So
Yeah,
that is something that needs to be looked into more. But yeah.
right. Very cool. We also have a question from Larry Lyons. Larry, if you'd like to unmute.
Yeah, I just unmuted. Hey, enjoyed that. You're working with Ying Zhou still, I presume?
Yes, I am.
Yeah, that's great for you. I just one topic I didn't hear you mention was anything about the difference between like the F region and the E region. Yeah, the F region you get the much stronger, faster response. The E region is slower, except where you've got aurora, and then that can really affect the currents and stuff. So just curious whether you've thought about that or have any plans to think about that.
Yeah, I have thought about it. I haven't looked into it personally myself, but it would be interesting to take these same events and sort of apply the same methodology to the E region, because all of the SDIs and Pfizer, they do take E region measurements as well, and kind of see the difference between them. So that has something I have thought about, but we haven't applied it yet. Yeah.
Yeah, if you decide to do it, it should be interesting. Just yeah,
Yeah, it would be.
where,
Yeah, thank you.
particularly where the aurora is.
Mhm.
Right. Excellent. Well, thank you again, Catherine, for a very cool talk. We'll be following this up next week with a talk from Daniel Gershman, and he'll be talking about external energy inputs into giant planetary magnetospheres. So thank you again, Catherine, and I hope everyone has a wonderful week.
Yeah, thank you.